The final item here to look at is the memory model. So OpenMP assumes and supports a shared memory model. Variables are stored in shared memory. All threads share an address space, but it can get complicated, in particular because we have cache memories and also processors are pretty advanced and try to reorder things to make performance be better. Multiple copies of a data item may be present in different levels of caches or in registers inside the processors itself. So in this case we have a variable A in memory here, and this can be in the cache. It could also be in a register here, and so on. OpenMP supports a relaxed consistency shared memory model. This means that threads can maintain a temporary view of shared memory, which may not be consistent with what other threads see. And these temporary views are made consistent only at certain points of the program. And the operation which enforces this consistency is called the flush operation. The reason for allowing a temporary view of shared memory, which sounds counterintuitive, but there is a good reason. And that reason is because you can allow then compilers to reorder things that can be reordered in order to get better performance. You allow compilers to temporarily store shared variables in registers, otherwise it would not be possible to store them in registers, and other things. You allow some hardware optimizations. So the flush operation defines a sequence point at which a thread is guaranteed to see a consistent view of memory, meaning that all previous reads and writes by these threads have completed and are visible to other threads, and no subsequent reads and writes by this thread have occurred. So it's analogous to fence in other shared memory APIs. So we have implicit flushes for all variables when you enter and exit parallel regions at barriers, both implicit and explicit, when you enter and exit critical regions, whenever you set or unset a lock, but not at entry to work sharing constructs or entry, but at exits, or to entry and exit of master regions. Okay? So here's an example why it can be useful. So this is a piece of code which is tempting to write if you want to write some kind of producer-consumer pattern. You have thread 0 that produces some data into variable A here. And then you set a flag to 1 to denote that this value of A has some valid value. Then you can assume that you have another thread waiting to consume the value A to do something with it, so it spins on the shared variable flag, and until this flag is, while this flag is 0, you just spin here and wait here, and when flag becomes 1, you know that A has correct value, so you can safely read it. Or, no. With modern day processors, compilers, this is incorrect code, also with OpenMP, although this code does not have any OpenMP statements in it. Why is this so? Well, if you look at thread 0 here, you see it only contains, if you disregard sort of what's happening inside the foo function, it only consists of two store operations. You store A here, and you store flag. You store something to flag. And if you're putting yourself in a compiler's perspective, a compiler does not know of any other threads that these two variables happen to be shared variables in a parallel program. So, from a compiler perspective, these two statements are completely independent. There is no dependence at all between them. So the compiler could decide, okay, it makes better sense to do the storing of flag before the storing of A. So let's do that. So it reorders it. Similarly, for thread 1 here, this is basically a repeated read of flag, and this is a read of A. And they are not dependent on each other. So the compiler can decide, let's do the reading of A before the while loop. There are some reasons that make sense for that. So this is one problem. The compiler can reorder stuff. Actually, the hardware can reorder stuff also. Another problem is that compiler may decide that A and flag should be allocated in a register instead of in memory. It's perfectly okay from a sequential program standpoint to do this here. So storing of flag here could be done in a register, which means that thread 1 will never ever see it. And by the way, the reading of flag here could also be done in a register, which means that this while loop will never exit, because there is no other way that some other processor or thread can affect the value of thread 1's register's content. So register allocation is another reason for why this code wouldn't work. So the way to make this work, if you would like to do it, because it's a pretty dangerous kind of code to program and difficult to program, is to use the pragma OMP flush, the explicit flush directive. And here is how you do it. So this is the same code, and we have added 4 flush statements here. The first one here, we specify which variables are to be flushed. You could do it without specifying anything, that's okay. But I've added the names of the flushes here because then it might be a little bit more performance than otherwise. So first you need to flush A, of course, because you need to make sure that A is written back to memory so that thread 1 can read it. But this is not sufficient. You need to have flush flag also, because this will prevent the reordering of storing to flag and A. Otherwise, the compiler might still decide to hoist up the storing of flag before the storing of A. So flush A and flag is needed here. The second flush here only pertains to flag, to make sure that flag is written back to memory. That's all that's needed here. On thread 1, when inside the while loop, we need to make sure we do a flush of flag. Why? Well, you need to have it here so that it will not do it in the register. We need to make sure that it reads from memory and nothing else. Flush flag. Before we read A here, we need to do a flush of flag and A, which is hardly visible here. Flag and A. And this, in this case, it's to prevent the reordering of the reading of A and flag. And now we have a functioning code that works with point-to-point synchronization, and we have a working code.